The aim of my presentation is to study the influence of wear area on the wear area dynamic and the acceleration of the axial box. My name is Zhou, come from Southwest Zhao University. My presentation is composed of 5 parts: introduction, the transient loading contact model, wear area vertical dynamic contact force, axial box acceleration, conclusions. Resistant wears, which have a rubber layer between the rim and the web, have drawn great tensions in the railway industry due to its characteristics of low noise emission. They have been used on many tram lines and some rail transit vehicles. Currently, many Chinese metro lines have solved several rail corrugation, causing abnormal vibration and noise problems in the vehicles and tracks, such as the fracture of the primary spring and the fastener clip. As a post-book countermeasure, the resistant wear have been proposed to reduce the vibration of the causing by rail corrugation. The 3D rolling contact model has been established to study this problem. This model has been further developed to take into account of the resistant wear. The upper 2 figures show the details of the mesh, and the mass of the resistant wear is about 20% larger than the rigid wear. These lower 2 figures show the geometry of the rail corrugation applied in the simulation. The left figure shows the geometry along the longitudinal direction. The corrugation is simplified as the sinusoidal in shape. The right direction shows the cross-section of the corrugation, and the max depth of the corrugation appears on the wear rail contact central point. Based on the field observation of the metro lines, we choose these 4 types of wavelengths used in the simulation. And at the speed of 80 kilometers per hour, the excitation frequency of the corrugation are calculated as this. By using the transient loading contact model, we study the influence of the resistant wear by comparing with the rigid wear. Firstly, we give the vertical dynamic contact force, which is a significant consequence of the wear-rail interaction. The dynamic forces are calculated by subtracting the dynamic force from the smooth rail from the corrugation excitation. The latter figure shows the dynamic force under the corrugation with the wavelength of 31 millimeter and 200 micron depth. It is seen that the resistant wear can effectively reduce the dynamic force, and the max reduction is about 22%. We further investigated the effect of wavelength and depth on the dynamic force. This figure shows the variation of the dynamic force with the wavelength. It is seen that the shorter the wavelength is, the greater the max dynamic force becomes. This is because the short wavelength means the higher exciting frequency, which leading to the stronger wear-rail interaction. It is further seen that the resistant wear can effectively reduce the dynamic force under corrugation excitation with the short wavelength, where become negligible with the long length. This is related to the radial decoupling frequency of the resistant wear, and we will show later. By using the FFT transformation, we can get the spectrum of the direction of the conductor force. For the wavelengths of 31 millimeter and 125 millimeter, the excitation frequency is this and that. At the corresponding excitation frequency for the 31 millimeter wavelength, the dynamic force is reduced by the resistant wire about 22%. And for the 125 millimeter, the dynamic force is increased about 32% when the resistant wire is used. This is related to the first order radio resonance frequency of the resistant wire, and the resonance frequency is about 390 Hertz. When the excitation frequency is higher than 390 Hertz, the rim and the web of the resistant wire is largely decoupled by the rubber. So the unspring mass of the resistant wire is just a rim, and the decreased dynamic force is found. When the excitation frequency is lower than 390 Hertz, the rim and the web behave like one mass. So due to the larger mass of the resistant wire, the unspring mass of the resistant wire is larger compared with the rigid wire. So the increased dynamic force is found. This figure shows the dynamic force, the variation of the dynamic force with the depth. This means that the max depth dynamic force increases with the depth for both wire types, and the effect of the resistant wire also becomes significant on the deeper corrugation excitation. The left figure shows the spectrum with different depths. And we can see that at the corresponding excitation frequency, the resistant wire also decreases the dynamic force by 20% to 30% compared with the rigid wire. Let's move to the axial box vertical acceleration. It's a little unclear, sorry. This figure shows the axial box acceleration in the vertical direction with 2000 Hertz low-pass filtering. And the acceleration changes periodically, similar to the corrugation. And for the wavelength of 31.5 millimeter, the resistant wire can reduce the acceleration by 20%. When for the wavelength of 80 millimeters, we can see that the acceleration of the resistant wire is even higher. This is due to the axial box of the resonance of the axial box. The latter figure shows the spectrum characteristics. We can see that for the 31.5 millimeters wavelength, the max acceleration occupied at the excitation frequency of the corrugation. Other peaks corresponding to the axial box resonance. And we mentioned that before, the first order decoupling frequency of the resistant wire is about 390 Hertz, and the theoretically vibration isolation frequency of the rubber is about 550 Hertz. So about 550 Hertz, the resistant wire can effectively reduce the acceleration of the axial box. And some other these frequencies, the resistant wire is the acceleration of the resistant wire is a little larger than the rigid wire. This is due to the influence of the resonance of the axial box. For the 80 millimeter wavelength, the resonator can also reduce the acceleration of the axial box effectively above 550 Hertz. It's worth noting that the excitation frequency of the calculation with 80 millimeter wavelength, the excitation frequency is about 278 Hertz, which is lower than 550 Hertz. So the increased, though the acceleration is slightly increased. We can also see that the max acceleration of the resonator wire is about 556 Hertz, just near the frequency. This frequency is the second order harmonic wire interaction excited by the corrugation. And this is due to the fact that the resonator wire axial box has a resonant model at 554 Hertz. This frequency is about, and this is excited by the second order harmonic wire force to resonant. So the max acceleration of the axial box is found. Also, we can see, so this leads to this figure, the resonator wire. The acceleration of the resonator wire is larger for the wavelength of 80 millimeter. But generally speaking, we can say that just the resonator wire can decrease the acceleration of about 500 the vibration isolation frequency. Conclusions. First, the resonator wire can effectively reduce the dynamic wire force with wavelengths, with short wavelengths. Secondly, the resonator wire can reduce the axial box acceleration above the frequency, above the vibration isolation frequency effectively. In the future, we can use this transient loading conductor model to design of the resonator wire. That's all. Thank you for your attention.